we are once again. Welcome to the physics video lecture. This is Physics 107B, video lecture 23. So we're starting our last chapter on special relativity. We actually had sort of a relativistic expression the other day when we were talking about radiation reaction. Maybe I'll put this up here, plug some numbers in for you guys. So what we had found, just to remind ourselves, so classical electricity and magnetism breaks down when, for wavelengths that are on the order of q squared epsilon naught mc squared. So we had that mc squared in there, and we were requiring that lambda be much less than this for in order that our radiation reaction force was small compared to the other field forces. Okay. So all right, breaks down when lambda is like that. And the thing is, if we consider energy on the one hand just of a spherically symmetric charge distribution being on the order of q squared over epsilon naught r, so that's the radius of the charge distribution on the one hand, and energy being equal to, or let's just say on the order of mc squared, that's the relativistic expression. So if you equate these two and then solve for r, that's what you get. Okay. So then you get this r, and we could even, well, no, we define it as equal, right? Q squared over epsilon naught mc squared. So suppose we plug in the electron, or say the proton charge, proton mass, epsilon naught, speed of light squared. So I'm just going to write here for the proton, because I did plug in those numbers, and I get something on the order of 10 to the minus 17 meters. So the electron's a lot less massive. You'd probably get 10 to the minus 14 meters. And those would be the lengths at which classical electricity and magnetism breaks down. So for wavelengths much greater than this, then we have consistency, and all of our formulas give reasonable results. So yeah, I just plugged these in. You guys can too, see what you get. But anyway, this mc squared, that's a relativistic energy expression, and we're going to run into that in this chapter now, figure out what it means and where it comes from. Yeah, so today we won't get there, but we'll talk about the relativistic kinematics. So we'll start just with the chapter on relativity now and see how far we can get. So we start with Galilean relativity. So let me see what I have here on our list. Good. So instead of relativity, I should write special relativity. So we've already had a relativistic theory in classical mechanics, but it was what we call Galilean relativity. So Galilean relativity is that classical mechanics equations of motion are invariant with respect to what's called a Galilean transformation. Namely, if we have the following, put it this way, laws of mechanics, and we're saying classical mechanics now. Laws of mechanics are the same in inertial systems. So an inertial system is one in which a force-free particle remains at rest. So I'll write that, inertial, force-free. So that means if you have a truly isolated particle, which means there's no force on it, particle CLE. Isolated particle at rest remains at rest. At rest. And then our transformation would look like this. R prime would be equal to R minus Vt. T prime is equal to T. So what I'm discussing here is the transformation between coordinate systems that differ by a constant velocity times time. So you take a coordinate system and you take, this one is named K and this one is named K prime. I'll put the K prime somewhere else. This is your K, this is your K prime coordinate system, and we'll just take a vector V times T from one origin to the other, and no rotation implied, just translation. And that means the vector in the R prime is R minus Vt, or it's just as clear if you say that vector R with respect to this coordinate system is the R prime vector plus this V times T vector, okay? So that's clear enough. So this is the transformation from one coordinate system to another, and the coordinate systems are moving with constant velocity with respect to each other. So I have to write this capital V here is a constant vector, constant velocity. Good, so under these circumstances, we have Newton's law. So in our system K, we have, say, m sub I, r sub I, second derivative is equal to f sub I of r1 to rn, right? So we've got an n particle system, they interact with each other, and it's an n particle system, it's an isolated system. Therefore, this f sub I is of the form, I'm just going to write here, r sub j minus r sub k. What I mean by that is that the interaction forces between the particles are based on the difference vector. So then if this thing is translating, if this system is translating with constant velocity, these difference vectors remain the same. So that's why in K prime, we would have m sub I, r sub I prime, second derivative, that's prime, is equal to the original m sub I, r sub I, second derivative. Because we're taking two derivatives, one derivative you have a constant, and the second derivative the constant's gone. Okay. So that's what it means to have relativity in standard classical mechanics as we've studied it up until now. There's another aspect of what we would call Galilean relativity, and that is the addition of velocities. And in fact, the addition of velocities seems completely trivial. But let's write down what we're actually claiming there. So Galilean relativity, addition of velocities. to show this, you know, the idea of somebody on the back of a pickup truck. Okay, so someone's standing in the back of a pickup truck that's moving along, and you throw, you know, you launch a ball forward. Okay. Throw a ball in this positive direction here, and then the speed of the ball is the speed that you had imparted to it, plus the speed the pickup truck had, and you're not going to consider any wind resistance, okay? So the addition of velocities, first of all, talking about that there, we would have, just by taking a derivative, v prime is equal to v minus capital V, taking derivative of the first equation there, or the velocity, say, with respect to the ground is equal to the velocity of the truck plus the velocity thrown, you know, when you throw something with respect to the truck. So this example is a good one. Throw a ball from the back of a moving truck. A moving truck. And this one I can say, and I'll just use the magnitudes. So V of the ball with respect to the ground is equal to this capital V. That's the truck with respect to the ground, plus V of the ball with respect to the truck. Okay. So yeah, that seems completely intuitive. Good. So those are the features of Galilean relativity. You've got this basic addition of velocities, and you have the fact that the laws of mechanics, Newton's law, mass times second derivative, are the same in these inertial systems that are translating with respect to each other with constant velocity. Good. So now we have to move to electricity and magnetism. So in electricity and magnetism, we discovered electromagnetic waves. And the idea of the waves with their wave speed seem to indicate or follow the same formalism as waves in a medium. Okay. So the pioneers in electricity and magnetism thought there had to be a medium that would carry these electromagnetic waves. So let's go ahead and start here. Electricity and magnetism. We have waves with speed c, right? We've talked about the speed of light. I'll write that out, speed of light. And we'll go ahead and just talk about the speed of light in vacuum. Question of what carries the waves? The ether, some medium, because waves in solids, waves in fluids prior to electromagnetic waves had to have a medium to carry them. Okay, so what carries the waves? And if they are carried in a medium, then we're thinking of a similar situation to here where there's going to be an addition of velocities. Now, we'll go straight to the Michelson-Morley idea because we can relate it to that picture up there nicely. So the Michelson-Morley experiment, the idea is the following. This is a fixed star. And let's put our Earth and our solar system over here. So here's the sun, and we've got the Earth orbiting the sun like this. Okay, so Earth, and let's go ahead and make it counterclockwise. So here the Earth is moving away from a fixed star, and 6 months later, it's moving towards a fixed star. So if the wave is being carried in a medium, then when you're moving towards the fixed star, you should measure a different wave speed, different speed of light than when you're moving away from it. That's the whole idea. Okay, so put that fixed star way far away. So just the idea the light's coming in parallel, moving towards it versus moving away from it. So I'll call this point A and this point B. So right here moving towards our light source, which is some fixed star at great distance, and over here we're moving away. And we're expecting to measure V light should be C plus V orbit. So the light speed should be the speed of light that, in vacuum that we, from our fixed coordinate system, plus the orbital speed because we're moving towards it. Here it should be the opposite. V light equals C minus V orbit, because we're moving away, we're outrunning the light, or trying to outrun it. So that is the expectation. Right. We expect to measure a faster speed, we're moving towards it, just as with the normal relative speeds we were talking about up there. Slower speed when we're moving away from it. However, what happens is, because the speed of light is so great, this whole idea of this experiment requires some sophisticated interferometry, which came around, around the turn of the 19th to 20th century. So that was the expectation, but what actually was found was that you always just measured C regardless. Okay, so this speed of light measurement from this distant source here, whether you're moving towards the source or away from it, you're always just measuring C. So Michelson-Morley find that V of light equals C always. Right, 3 times 10 to the 8 meters per second, regardless of relative motion. And if you go back to our pickup truck idea, instead of throwing a ball, imagine we're shining a flashlight. Okay, so we're shining a flashlight, and we're going to add the speed of light, the speed of the light plus the speed of the truck. Except when we receive the light over here, we're always just measuring C, regardless of whether the truck's moving towards us or moving away from us. Okay, that's the idea here as well. So the addition of velocities did not work. Okay. so we'll have to write that down. So let's call it the Galilean addition of velocities did not function. Was falsified, whatever you want to call it, falsified. Okay. Now I have the actual relativistic formula here that I think I'll bring into play. Okay, no, at this point, with this contradiction here, Einstein steps in and we have his postulates of relativity. So yeah, what failed was the addition of velocities. So next, the Einstein postulates. Two in the way we write this down. This is about 1905. So the first one is a generalized principle of relativity, that the laws of physics, not just mechanics, the laws of physics are the same in inertial systems. So the first thing we call the principle of relativity. Laws of physics are the same in inertial systems. So laws of physics apply in all inertial states. And the second principle is that the speed of light, basically the speed of light, he formulates it this way: the speed of light is a law of physics, okay? And so you're going to measure the same speed of light in all inertial systems as well. So, universal speed of light. So the speed of light in vacuum is going to be the same value regardless of your inertial system. Speed of light in vacuum is the same for all inertial observers. Okay. Regardless of the motion of the source. And so this second postulate is clearly in violation of the Galilean relativity, except the Galilean relativity is in violation of reality, okay? So we'll see what happens with the second postulate here. And the first one, this has as a consequence, I'll formulate it right now, and then we'll derive it. So I'll write it down first, we'll derive it in the course of the hour. So this is the relativistic addition of velocities. Again, we'll put it down right now and we can compare it to our flashlight on the truck, so we'll have a good example right away. So what we have is VAC is equal to VAB plus VBC. Those would be my expressions. Before, this would be the Galilean version of our throwing the ball off the truck. Okay. The ball with respect to the ground, the truck with respect to the ground, the ball with respect to the truck. Okay. Did I have that right? with respect to the ground, truck with respect to the ground, ball with respect to the truck. We could have it that way. Okay. And then we'll have here 1 plus VAB times VBC, two velocities on the right side divided by the speed of light squared. So we're going to derive that, but right now we just want to see that it solves our conundrum. Namely, what if instead of throwing the ball, we actually have that flashlight with the speed of light beaming out. So then one of those speeds is c. So now suppose VAB is equal to the speed of light. Okay. Then, as we measure it, we get C plus VBC. Let's make sure that's V sub BC divided by 1 plus C times V sub BC divided by C squared and that simplifies. We actually simplify that right there. Then we end up with C plus V sub BC in the common denominator of C. These two cancel and we're just left with the speed of light. So there we're measuring the speed of light of that beam off the back of a moving truck, and we're measuring C, even though we've got that truck moving with V. Okay. So that right now that's the proof that the relativistic formula solves that conundrum we had. And now we have to go back and actually derive everything. So we've got the Einstein postulates, we've got that example. So now we have to go back to the principal problems here. So we're going to make use of these postulates here. The first thing that happens is that the concept of simultaneity has to be modified. Simultaneity. So when do two things happen at exactly the same time? And what's nice here is because Einstein did his work, around 1905, the best example of a constant velocity object was a railroad car. So you get to consider railroad cars rolling along a very nice, straight, smooth track. Okay. So what we're going to have is a railroad car of length L, and we imagine, and it's moving with a constant speed, and we imagine some light goes off, a flash of light, at some time, and then the light's gonna end up at points A and B. So if we're right here smack in the middle of the car, and we're at point A, or we're at point B, the light arrives at point A and B simultaneously, if we're in the car. And the question is, what does the outside observer see? Well, for the outside observer who's standing here on the bank, on the embankment, actually he's looking at the car, not us, but for the outside observer, the flash here happened at time t equals 0, and point A was running away from the light, point B was running towards it. Okay, so it got to B before it got to A. Okay. For the inside observer, the car's moving, he's in his own reference frame, can't even see outside. And for the inside observers, the light reached A and B at the same time. So inside, you have simultaneity. Outside, it's not simultaneous. But the law says that we've got this universal speed of light and this principle of relativity, so there is no preferring the one over the other, right? The concept of simultaneity has to be dropped or modified. So, do we put anything else down here? I'll just put this in words. So we've got light flash in the car, reaches A and B at the same time. So in the car, reaches A and B at the same time. And yeah, if you're in the car and it came right from the middle, you just back calculate the time. If it reaches you and it came from the middle, you just back calculate the time at which it was emitted, okay? But again, for the outside observer, the car, this side is running away from the light, this side is running towards it, so it's not simultaneous. So, for the outside observer, light reaches point B first. Okay. So if these events are simultaneous inside the moving car frame, at the outside observer frame, they're not simultaneous. And we have to leave it at that, okay? Because we're asserting this universal speed of light and this principle of relativity. Okay, so from there we can go to time dilation. We can make this this idea quantitative. So time dilation. Once again, we've got our railroad car moving to the right with speed v. It's on the track here. And now what we have is light that's going to flash up from this corner here, and the height of the car is h. And so in the car we can say C, so in the car, C times delta t prime, so that's the prime coordinate system, it's the one that's moving with respect to the bank, is just going to be equal to h. How about a red here? And so then we've got the light hitting the bottom there, C times delta t prime. And if I want, I can actually have it bounce back and do the same thing with 2h, okay? Well, right now I'm just calling it from top to bottom here. Okay. So that's in the car. What about our outside observer? Well, the outside observer sees, as the car is moving forward, and it's going to hit right here. Okay. So we have with a very high speed. Okay. So this is going to be a v times t, but the c times delta t is going to be along the hypotenuse. So let's go ahead and calculate that. So in the car, c times delta t prime is h. Outside observer, we have c delta t squared by the Pythagorean theorem is h squared plus v delta t squared. And we'll solve for delta t squared. Times c squared minus v squared. Put this over here is equal to h squared. But our h squared is going to be c squared delta t prime squared. So now we can solve for delta t in terms of delta t prime. And I'll do that up here. So delta t will be, right, h is gone, will be divided by delta t prime square root of 1 minus v squared over c squared. Yeah, square root divided by, and we have that. Okay. So that's the time dilation formula. And again, what are these two delta t's? The delta t prime is the time that you measured inside the railroad car. So that's your clock ticking at the rate delta t prime. Delta t is measuring the same process, but it's moving with respect to us. And you see delta t measures a larger time because this denominator is less than 1. Therefore, the outside observer sees the clock running slower. Okay. And for the outside observer, it's a moving clock, so we can say the moving clock runs slower. Okay. So there's the time dilation formula, and it really just made use of the Pythagorean theorem. Now I should note for remember I said we could have, it would have given the exact same result if we had it be 2h and then it would be like that. Okay. It would reflect back up to there in this other frame, bounce back over. And that's kind of an important point because the observer in the car has one clock. Okay? The outside observer, to actually make this observation, has to have made a measurement here and then a second measurement there. So the measurement at the first place is said to have been measured by a clock that's located there, and the second location has a second clock. So the process is not fully symmetric in the sense that it's the person who sees the moving clock that sees the time dilation, that sees it moving slower. If you reverse the situation and you had the person inside the car here viewing the process out on the tracks, it would be the same formula. It would slow down. It would slow down for the person who's making the measurement with two clocks instead of one. So that's a subtlety there. Otherwise, you'd think there's a contradiction. So yeah, you see the clock going by. This Pythagorean theorem tells you it's going slower. Okay. You do the same thing as an observer from the moving car, because it's a constant velocity. You're going to get the same formula for the clock outside the car that you're observing. Okay. So yeah, that's an important point. See if I can characterize that somehow. Yeah. So I'll put this as an important note. The moving clock runs slow for either observer. The one who's observing the moving clock, for whom the clock is moving, has to basically make his measurement with two clocks in his reference frame. Okay. An important point, so we have that. Next, we do the Lorentz contraction. So this was the time dilation. Lorentz contraction. So this time, we're going to imagine, we're going to actually take the same railroad car, slightly different configuration. Lorentz contraction. So yeah, we've got the railroad car. This thing really does best example, yeah. So we've got the railroad car moving to the right here with speed v, and this time we're going to bounce light off the other edge. So imagine send light here, have it bounce back, essentially back to its original point. Okay, and we've got a length L here. Okay. So since the car is moving forward, we get the time for the path. So yeah, the light's, I have my note, the light is reflected back. Okay. So light reflected back. And now we'll just calculate the time for the light to go hither and thither. So on the one hand, I'm using delta x here, I may as well do that. So delta x is that length there. So we have for the forward trip, delta x over c minus v, and for the return trip, delta x over c plus v. Okay, so forward and return. Because this time is somewhat longer because we're running away from the light, and this one is somewhat shorter because we're approaching the mirror from there. Okay. So that can be simplified to c plus v delta x plus c minus v delta x. So we end up with 2c delta x in the numerator, and we got the difference of squares there, so c squared minus v squared. So that's the light reflected back. Next, we're going to use the formula up there for the delta t. Okay, good. So that's the one thing. Now the second point was inside the car. Inside we have it easier. We just have c delta t prime, so the inside the car is the prime, the moving system is just equal to 2 delta x. Okay. So now we can put these together. We have our delta t, we have delta t prime over root 1 minus v squared over c squared equals 2c delta x over c squared minus v squared. And we can say the delta t prime is 2 delta x divided by c over root 1 minus v squared over c squared. On the right hand we have a 2c delta x prime inside the curve. And then we have 2c delta x over c squared minus v squared. Good, so the 2's cancel. We can multiply top and bottom by c. We have a c squared. We can divide by the denominator. We get 1 minus v squared over c squared. So this thing here gives us delta x prime over root 1 minus v squared over c squared is equal to delta x over 1 minus v squared over c squared. We can cancel the square root, and we get delta x prime is equal to delta x divided by root 1 minus v squared over c squared. So this is the Lorentz contraction. And again, let's remind ourselves what these unprimed and primed quantities mean. This was the length of the car as measured from inside the car. So I'm riding in the car, I've got my meter stick, I measure the delta x prime. Okay. Delta x is the length as measured from outside the car. So delta x, solve for delta x, it's this measurement, with the meter stick times root 1 minus v squared over c squared. So that's a contraction. That's why we call it the Lorentz contraction. So yeah, the moving meter stick is measured as being shorter. So instead of a railroad car, we're just sending this meter stick along. Outside, observer measures it as being shorter, even though for me it's a meter stick. But if I'm moving with it, you see it as shorter. Same argument holds though. If I'm moving and I observe something outside, same argument holds, and I observe that as moving, as being shorter. So the moving object is contracted. So that's our Lorentz contraction. So with the time dilation and the Lorentz contraction, we can get the full Lorentz transformation. So yeah, I'll just put this as a note. Moving car is shorter. The paradoxa that apparently come up are always resolved by actually fundamentally by the simultaneity difference. Because you have that lack of symmetry, the one measurement of the moving object is done with 2 clocks, whereas the measurement in the moving object or in the frame of the moving object only needs 1 clock. Okay. So yeah, let's go ahead and write down, speaking of clocks, I better consult the clock here. Okay, Lorentz transformation. So for this transformation of coordinates and times, we're going to stick with the motion in the x direction. So Lorentz transformation. So again, we have our coordinate system. I'll just draw the x and the y. This is the system K. We've got VT, and we've got the x prime and the y prime. And we'll let the origins coincide at t equals 0. Origins coincide at t equals 0. And so now we want to transform the coordinates. So the Galilean, it's not a t, the Galilean transformation is, as we saw before, x prime is equal to x minus vt, y prime is y, z prime is z, t prime is equal to t. Right? So we were just transforming along the direction of motion. So next, let our meter stick be in the moving coordinate frame. X is equal to d plus v times t. So the end of the meter stick, x is at d when time t is equal to 0, and the other, the other end is at the origin. Okay, so we've got a meter stick that's moving, and at time t equals 0, the end of it is at point D. But the length is contracted. So what we have is D is equal to x prime. Oh, I didn't introduce the gamma yet. Gamma. This is for good shorthand, where gamma is 1 over the root 1 minus b squared over c squared. Actually, we saw that the other day in one of our problems. So now we can immediately get the x, y, and z of the Lorentz transformation. We'll have to work on the time, which we're going to use this, but I got to erase this. Okay, so we have that. So now x is equal to x prime divided by gamma. Okay, and that gamma is 1 over root plus b times t. Okay, so we're really using this idea. X minus vt, bringing the vt over the other side, so x prime. But since we have that length contraction, we've got the x prime over gamma, which is x prime times, right? So we've got the contraction. And now we just solve. X prime is equal to gamma x minus vt. So that's the difference between the original Galilean transformation and the new relativistic transformation, based on the constancy of the speed of light. And of course, when v is much, much less than the speed of light, this essentially just turns into a 1, and you're back to where we were before. So we can write y prime z prime equals z, because nothing's happening perpendicular to the direction of motion. The t prime, we have to make use of the time dilation formula as well. Okay. So next, transformation of the time. So we had we're going to use the x prime here. We have x prime equals gamma x minus dt. But now we have that symmetry between the observers, but the symmetry of the observers means we have the same formula where we just switch the primes and reverse the direction, the relative motion. So v, replace v with minus v, so that we end up with an x equals gamma x prime plus v times t. And now we just have to remove x from this equation, and then we'll have t, actually remove x prime from these two equations, and then we'll have the t prime remaining in terms of forgot to put a prime here. Okay, there's the symmetry of the observers. So we've got the x prime this way. In the other coordinate system, we're looking out at x, and then so it's x prime and t prime. So we're going to solve for t prime. Solve for t prime in terms of unprimed quantities. So what we're removing is x prime from these two equations. Quantities. And that's just a few lines of algebra. Okay. We got these two equations. We're going to solve for t prime. Two equations eliminate the x prime, and we end up with, should I put it down there? Yeah, we'll do this. So t prime is equal to gamma t minus vx over c squared, just by that algebra. And in fact, I'm going to go ahead and put that here. Gamma t minus vx over c squared. So yeah, that way we've got our Lorentz transformation right here. Motion in the x direction, primed and unprimed system, right? We got this x with the replacing the prime and the unprimed and the replacing v with minus v by just imagining this system moving to the left with respect to that system. Okay, we'll just rewrite that Lorentz transformation. Now what I finally want to do is get the addition of velocities. That's our last task. And then we'll have everything we set out to do in this hour. So and for that I just need this right here. Addition of velocities. And yeah, so I have my k and my k prime. Oh, this one was k prime. moving coordinate system with respect to each other. So in K, we'll just have dx dt will be this called u, okay? In K prime, we'll have our u prime is dx prime over dt prime, okay? And now we should have everything we need. Yeah, so the dx prime, we'll just treat these differentials algebraically. So we've got the dx prime, we'll have gamma dx minus v dt as a differential. And for the dt prime, we'll have gamma, we're using that one right there, or actually right here as well. We'll have gamma times dt minus v dx over c squared. Okay. So that's going to be u prime, the velocity in the prime system, in terms of now the unprimed quantities, so we can continue with canceling the gammas and divide top and bottom by dt. So we have a dx dt minus v divided by 1 minus v over c squared dx dt. And then we can just put the u in there. So what we have now, so dx dt was equal to u. So I'll go ahead and put it here. Spin it with u prime is equal to u minus v over 1 minus v u over c squared. And we can do the same thing we did before with the symmetry in the situation. We can solve for u instead of u prime by replacing the, exchanging the primes and replacing v with minus v. So also, we will have u is equal to u prime plus v over 1 plus v u prime over c squared. And in fact, I'll put a box around this one, they're both equally valid. This is the one we started with at the beginning of the hour when we had our signal moving with the speed of light. And so you'll have the same thing if you replace u prime with c, okay. Then you'd have c plus v, vc, yep, same thing, okay. Good, so we've come full circle, so to speak. So those are the basics of the relativistic kinematics, derived on really, physical, intuitive principles, intuitive as it can get in this regard. So what we'll do next time is pursue a slightly more advanced formalism for this, but with the same physical content. And we also have to move into the relativistic dynamics. Notice there hasn't been any force, there hasn't been any mass in here yet, so we still have a ways to go. Okay, see you then.